Chen from Boston College, who's going to talk about counting curves in critical locus via logarithmic compactifications.
Thank you for the invitation. Actually the title of the paper is the logarithmic gauge linear sigma model. So one of the reasons when I sent my title abstract, I didn't send this because I'm not trying to understand a large part of it in this title, what is a gauge linear sigma model. Later on, I thought I understand it. After talking to Sleep, I figured that, but still get lost with the actual meaning of that. Okay, but at least there are two parts. One is logarithmic. And the other part is gauge linear sigma model. And from here, we need to relate to the actual title of this talk, which is counting curves in the critical locus. So we'll see how this fits together. Just a quick introduction of the first part. We're going to use logarithmic geometry to compactify certain moduli spaces. So what is the thing we consider in logarithmic geometry? So let X be a pair. So we call this one a log scheme, or a stack, or a log stack. If first this one is a usual scheme or stack. And second, this one is a sheet of noise. So if you work with scheme or the number stack, you can use a topology or analytic topology. But if you use arting stack, you use smooth or flat topology. So this will be a sheet of monoids with in appropriate topology. With the following conditions. So first, it is equipped with the structural morphism. So one, this sheet relates to the geometry of the underlying object. And second, it's related in this way. So the idea of this is to remember the boundary structure. Boundary structure is defined by equations that are not invertible. So for the invertible ones, you don't want to do any modification.
Alpha is a morphism of monoids.
I should say that this is sheaf of monoids with multiplicative structure. Oh. Right. This is a sheaf of this is a morphism between sheaf of monoids.
So the left is subsheet where star is subsheet as in this time.
Right. This is a subsheet inside here. Yes. Okay, so we have objects, we talk about morphisms. So what is a morphism? So given a log scheme or stack, and we want to consider the morphism between them. So every morphism is between log scheme or stacks is given by a pair. So the first one, F underline, is just usual morphism between the underlying structure. Underlying a morphism of schemes or a morphism of stacks. And the other one you should view as F upper star, like pullback of functions in the following sense. So I have a log structure on Y, and I can pull it back to X that defines a log structure with this structure morphism. And I have over x underline, I have this structure. So f flat is the sheaf of modules fitting this diagram. So that compatible with the underlying structure.
You check it locally.
Which
Check your loc. You check to check this property. You mean just cover locally? Yes.
yeah.
Just okay.
Exactly.
Yeah. So we don't need.
For example, you can think about this pair as a scheme with a toroidal boundary divisor. And Y is also a scheme with a toroidal boundary divisor. Then having a morphism like this means a toroidal morphism. The boundary has compatible toroidal structure. Okay, so let me give you two examples. So the first example is a trivial structure. So for any underlying scheme or stack, I can take the sheaf of monad to be vertical functions. So this one has no boundary. You can check that this is actually a log structure satisfies both in all cases. And a slightly more interesting case is the following. We're actually going to use this. So let's take X be a smooth scheme or stack. And over this, we take a divisor. So maybe for simplicity, let me assume that this is smooth divisor. Actually, you can take D to be a toroidal divisor. And then associated to this boundary, there is a natural log structure given by collection of all regular functions. Of course, you use a proper topology. And this function satisfies the condition that if you restrict it away from the boundary, it becomes invertible. And there is a clear injection as a sheaf of monad in the multiplicative structure to this, which is the structure morphism. And you check that this one is actually a log structure. So, so this example tells us that logarithmic structure you can really think of it as a pair which is a scheme with a toroidal boundary. But the real power of logarithmic geometry is it's in the degenerate case when the boundary is everything. How you're going to specify this? You need the sheaf of lines, because in that case you don't even have a pair from the underlying structure.
I have a question about this trivial log structure.
Uh-huh.
So how trivial is the case when mx equals ox?
That's a highly non-trivial case.
That's a highly non-trivial.
Because that monad, sheaf of monad, is not even finitely generated.
Oh.
It's huge. Yes. Right. Okay. So so now let me talk about the input data of log GLSM.
So here, in this simple case, this sheaf of monoids, isn't it just the ones having zeros along the divisor?
Having zeros along the divisor.
All twisted by minus. You can
Yeah.
say. Yeah.
You can have infinite dimension orders, larger than that.
Yeah, that's right. Yeah, okay.
It's finite, right? It's finite, right?
It's finitely generated, yes.
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 So in this talk, I'm only work with finitely generated data with nice kits.
Yeah.
Okay. So the input data of log GLSM gauge the linear sigma model. Okay. So let me put. So this will be the dream case we want to have maybe after another 10 or 5 or 10 years. But at this moment we couldn't do it. So what is a dream case? So we have some. So we have. Okay, I didn't invented this notation. Somebody else wants to use it this way, but I think it makes sense. Okay, so I have a morphism between log stacks. So this one is basically BGM, a point quotient GM, parameterized lamp bundles, but with trivial log structure. But this one has a non-trivial log structure. So this is a proper DM type morphism of log stacks. But this one has trivial log structure.
Trivial is just O star on C star.
See that again?
So trivial O star on C star, or just so on GM, yeah. You are on GM, yeah.
Yes, the log structure of the bottom has is trivial.
Yes, just Z essentially, yeah. On the
Is the structure
Invertible, yeah.
invertible elements in the structure?
invertible O is C star.
Yes, C star, yes, exactly.
Invertible O is okay.
But this one will have interesting
Yeah.
structure. And so this one parameterizes lamp bundles. So it has a universal lamp bundle, which is this one. And this one, as a log stack, it has an open substack consists of locus with trivial log structures inside that substack. In the open substack with trivial log structures.
From below. From below.
From here.
Yeah. Yeah, no, but it's trivial which is kind of coming. Which was below, yeah.
Yeah, also
Trivial part
from
is
below.
that.
Yes.
Trivial part is that. Okay. So what? Okay.
This also has a trivial logarithmic structure, and I have an extra morphism. So W is a morphism from a stack to another stack, with the property that the critical locus of W is proper over BC star R. So yes.
What's LR again?
This line,
LR.
LR is a universal lamp bundle over BGM.
Yeah.
So this one is what we call a superpotential. But from my point of view, it's really just a morphism between two stacks, with the actual property that the critical locus is proper.
Proper. What does it look like? Finite number of points or not?
Well, it can be very complicated.
Very complicated.
But in that situation, it recovers for morphism of the critical locus.
But it can be complicated. Some simply compact within C star. Yeah.
Say that again.
It is the subset of C star. Yes.
It is a subset of C star. No, in general not. This stack can be complicated.
That stack is just mapping to these
Yes.
stars. So this one is more complicated.
So this guy is Artin stack. This guy is necessarily an Artin stack because this morphism is proper fundamental type. Okay. Okay, so let me tell you the player in this talk called logarithmic R map. Definition: a log R map is a commutative diagram.
Some dimension. But that's what's different.
Yes, it's different. Yes, exactly.
I'm just confused. What is R again?
R, okay, so Yumi told me this. R comes from the physicist, from physics literature that R is R charge.
Or
So this tensor means some special tensor related to some actual structure.
So
Well,
this is just BC star, but R is just for
right.
name.
R is for a name. I have no idea where R comes from, but it certainly comes from physicists. Okay, so a log R map over a log scheme S is a commutative diagram like this, and this is family of log curve over S.
Okay. And that's what kind of family you have there, yeah?
Right, you need to fit into
So essentially you have a family of curve over the star with some degenerations, yes? Simple degeneration.
this curve is not over C star. This curve C is not over C star. I haven't finished everything.
Yeah, okay. Just to have
whether I put underline or not doesn't matter. So this is a log smooth family. Being a log curve, I'm not going to give the exact definition because we're not going to actually use it. But being a log curve means that you have an underlying pre-stable curve, and you also specify the first order deformation smoothing of the curve.
Yeah.
That is essentially the data of log curve. So once you specify the first order deformation, then this becomes a log smooth family.
Oh, yeah.
And the log smooth family has a well-defined log cotangent bundle.
Okay.
So if you look at the underlying family, the log cotangent bundle will be the dualizing sheaf twisted up by the marker points.
Yeah.
Okay. And this arrow is defined by the pullback of the universal line bundle here to that. So that's the definition. So if you look at other literatures of GLSM, the definition is quite involved. You have maybe a whole page of data you need to fix. But here in our case, this is our definition. So you can compare this definition with the usual stable maps in the Gromov-Witten theory. The only extra part is an arrow to this.
But you have to specify what is beta.
I haven't specified it. So that's why it's called a dream case.
But
Ours,
your curve is mapping to it. So what is it?
this is a log stack, this is a log scheme, so this is a morphism of log object.
Okay.
Yes?
Why do you insist that that be like DM? Why couldn't it be like sort of arc and sat? Like if you have a gauge linear sigma model, you have another like group action on vector
Okay.
space.
So you are asking something else. So in this talk, my morphism has no base points. That's the next thing that we're doing right now. So it turns out that with base point, we couldn't do it in a very general set, like consider complete intersection in every smooth variety for Gromov-Witten theory, because we don't know how to deal with base points for things other than GIT quotients. Okay.
But if I'm taking the gauge there, you consider like the map goes into the GIT quotient. It doesn't map into the. You don't have a definition that allows you to map into the actual like vector space mod group.
This includes that without base points. We'll see.
You haven't,
I'll give you.
you
a bunch
haven't
of
given
examples.
the beta. So.
I haven't defined exactly the beta we were going to consider. Actually, I don't think that this theory is going to work for actual data defined that way. You necessarily need some actual conditions on that. That's something we struggle for months.
Just a side question. You mentioned this log Calabi-Yau, but so this log Calabi-Yau, I mean, is it also true that it's an analog of theorem of like Professor Bogomolov on this smoothness of the moduli space? Is it also true for log Calabi-Yau? I mean, for deformation.
Log Calabi-Yau.
Yeah, you deform it. It's also smooth. I mean, at some point. We will look at this family.
So the goal of this is to compare with invariance of certain log invariance with certain Gromov-Witten invariance or usual Lambda-Ginsburg FGRW invariance, where the usual Gromov-Witten and Lambda-Ginsburg that doesn't involve any log. So there's no.
Oh,
not yet a
it's not to
log
the,
in this
oh,
picture.
I see. It's not to the.
But if we could fulfill the dream, that will include everything. But that will be
Not compute. Okay.
the topic of this talk. Okay. So I want you to compare this notation with the usual pre-stable map. How does this differ from usual pre-stable map, right? Usual pre-stable map will be just C maps to some target X. And now the new ingredient here is you need to have some differential forms that constrain your map, to trace your map. And somehow this makes everything work. Everything means you want to consider a computer intersection property of homomorphism invariance. And we will get to that later. Okay, so this is a dream case. Let me talk about the actual target that we're gonna work with today. So first, the curly X. This is a proper EM stack with projective cosmoduli state. We need that for defining orbital homomorphism invariance. This is a target. And now we need a vector bundle. So this is a vector bundle over the orbifold or the elemental stack. And it has a positive grading given by I. I is some integer. And we also need a lamp bundle over curly X. And finally, we need a positive integer R. Okay. So from this data, we'll construct a curly P that we're going to work with today. So to construct the curly P, we first have BC star R cross curly X. That has a morphism mapped to PGN, which is given by LR box tensor LQ. And then we take the rth root of this. Take the fiber diagram that leads to a very curly X. So over this very curly X, there is a lamp bundle that is the rth root of this by definition.
What is LR?
LR is the universal lamp bundle over BC star R. So you should think of LR, you should keep in mind that LR is just omega log. Everything is going to be put back to a curve. So you can think of the picture over a curve.
What is Qile in practice?
This?
Yeah.
This will be, okay, so this will be an ambient space. And inside the ambient space, there is a critical locus. And we want to compare the homomorphism of the ambient space with the homomorphism of the critical locus. That's the goal. But in this picture, there are two parts. One is the target part that will be with the modular space. That doesn't depend on W. And the other part is a W that is the critical locus controls the virtual cycle. So for the modular parts, we only need this part. We don't need this one.
So LR pulled back to the curve is the cotangent bundle with logarithmic zeros along marked points, right?
Logarithmic poles along marked points.
Logarithmic poles along marked points. And the marked points are different than the nodes for you.
Is different.
Are smooth marked points and
Smooth marked points.
and no nodes. You
No
don't
nodes.
consider
And
just the
nodes,
marked
this is a dualizing sheet.
Yeah.
Well, does your W, is it non-vanishing?
W is non-vanishing.
Is it or can it vanish?
Yeah, it vanishes somewhere.
So it's not a log map to A1 mod gem.
Both this and this of W has trivial log expression. So the whole point is, how to extend this W to here. That makes sense. Okay, so let me tell you the curly P that we're considering today, and I want to specify that there is a choice involved. So I'm going to take the weighted project bundle. The reason that there are stews comes from the traditional notation in gauge linear signal model. So it's not like that I want to make it too complicated. So what do I mean by this?
Can you explain everything?
Yeah, there are too many. Is this better?
Slightly.
Slightly.
Just one by one.
Okay, so inside here there is okay.
Okay.
So I have a project bundle.
Yes.
I compactify it by throwing infinity divisor.
I see.
The way I compactify it is that I make a choice of weight.
Yeah, I see. On any yeah, okay.
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 And I want to emphasize that this weight, I will tell you soon, depend on this I, and it's very important that we choose weights this way. Otherwise, the theory won't work. And this weight also depend on the choice of A that I'm going to tell you now.
Can we do an explicit example to see what they are?
Yeah,
And maybe from the beginning, intuition could work if you even said why is B zero, like beta zero,
Beta circle.
beta circle.
Beta circle is this guy.
I know, but I mean there are many other maps that map to N of R. So
Yeah, let me give you some examples so you see what it actually means.
Not too trivial.
Not
Not too trivial.
not too trivial.
Okay, just.
I think even the simplest example is not trivial. If you calculate the variance, actually there are something surprising.
Not trivial.
Not trivial, yeah.
Usual examples are pointed at me.
Well, even you take this one to be a point, there are non-trivial conjectures, and we actually prove it. We're gonna prove it. So the choice of the weight is given by I chose D to be the GCD of all i's here, okay? And I chose my A to be some fractional number here. And so the ith factor has weight equals A times I. So that's my choice of weight. So later on we'll see that why this, the reason that we need this choice of weight is because we want the W extends to infinity with the poles that we could control. Otherwise, or in other words, by this choice of weight, W becomes quasi-homogeneous. This is the choice of weight that make everything work. And I should say that this one is a logarithmic stack with log structure given by the smooth divisor, if I choose everything smooth. Okay. So I already defined what the target is. Now let's look at examples. So I want to roughly say that the examples includes all the FGRW theory or the lambda Ginsburg models. And it also includes all the P-field case. Okay? And let me be more specific.
Yeah.
So in special case of the non-logarithmic model or FGRW theory, it's the R-spin case. Let's look at the R-spin case first. So if you look at the input data, it's pretty trivial. Trivial anomalies.
So that's
Wait,
point. Okay.
Okay.
Something more. Yeah.
Yeah, but there are something interesting going on. Okay.
Okay.
So let's look at so I have EC star R at the bottom, and this one is a point, so this will be the identity. And then I take the R's roots of LR. That will be my curly X, which is another EGN. So now if I have C mapped to here with omega log, if I leave this arrow to here, that amounts to true the R roots of omega log. So that's the R spin structure. Okay. So so this is the R spin structure. And above this, what is this? So so the curly P is proj because the weight I chose 1. And inside this, the open part is LR. Okay, so what is an arrow from C to B circle? That is a section of the spin bundle. Okay, so not so complicated, but so the moduli space we're interested in is arrows from C to here. Right. The idea is this moduli is not going to be proper, and they want to compact that. Okay. So let's give another P-field case which relates to the homomorphism theory.
So geometrically compactified is about potential to a vibration to P1. What's happening, or?
Potential not to P1 because the target, this one, not always of rank 1, right? This is not always one dimensional vibration. It could have higher dimensional vibration.
I mean, it just means suppose potential is like a Cn to C. This is the map. It's a logarithmic polynomial.
Yeah.
It's a function on Cn to C.
Cn to C, yeah, in this case.
And then in this situation, when you compactify, does it compactify to something mapped to P1, or it's not like that?
It's related, but there are poles. You need to
Yeah, but infinity has some kind of a divisor. So.
Right. You need to think about how to deal with poles. And I'll give you a point example. And okay, so the P field is so let's deal with this one is a projective variety, and we have a vector bundle over X, and that shows R equals 1. So so BC star R, what is this? So my curly X, because this is identity, so curly X is just a product. So I have C mapped to here, which is omega log. If I want to leave this arrow to here, the extra part we need is a pretty stable map to X, nothing else. And above this, what do I get? I get this one, charge of EQ tensor LR with some O infinity. So inside this, my curly P circle is going to this. So now what is an arrow from C to here? So C to omega r is just omega log. But if I already have an arrow here, I already specify a stable, pre-stable map from C to X. And then along that pre-stable map, I can pull back E2. And from here to here, I want to take a section from C to the pullback vector boundaries. So this is exactly the P-field case formulated in by Chen-Li and many other authors. And since we talk about P-field case, let me just mention that we have another part of the data, which is the superpotential. Where did the superpotential come from? So suppose S is a section of P with a property that the vanishing locus of S is smooth of expected dimension. Okay. Then you look at S2, which is a function from the total space of E to C. And now you consider the critical locus of S2, that is this one. So let me call this Y. Now I want to put this picture to over this bundle, currently P circle. So my W will be S dual box tensor 1, which is from E dual box tensor LR to LR. So the critical locus of W is Y cross BC.
So you can then get, okay, so then you can measure the potential sections, something like that. Yeah. So now you cut into
Yeah. So, okay, so the idea is we're going to define some invariance dependent on ambient space X, and we want to relate it to the invariance of Y.
This new information is this classifying space.
Is what?
The BC star, I mean, this is new information.
Yeah, it carries
Compared
the
to
R, the actual trace compared to usual stable maps.
yeah, so TP4 case, TP4 example.
Mhm.
So the critical locus is the quintic, right?
It's quantity.
But
So
then
one,
what about the BC star in that case?
you know, this critical locus is inside this R piece.
Yeah.
So okay, so think about if I have an R map to critical locus, then to this piece is omega log. So the only data I need to determine an R map to critical locus is a stable vector 1. Okay. Okay, so I already tell you the objects, and I give you some examples. Then I want to talk about the moduli stack I want to work with. So in order to do that, I need to tell you the stability condition. So a log R map C to the curve T is stable if 1 F is representable. Like the orbifolds homomorphism case, you want to permanentize representable objects. And second, this is a non-trivial part. Omega log, say over S to to the 1 plus delta tensor f fullback of the polarization of the curly x of the target tensor f fullback O A times R times infinity. So this is for k sufficiently large, delta sufficiently small, and h, this is an ample Lemon bundle over the target or over the projective variety. So this is a part that we struggled for several months. Let me tell you what is the geometry behind it.
What is delta?
Delta is some very small number. K is some arbitrary large number. It looks strange, right? If you do Gromov-Witten theory, you won't see delta, and you won't see infinity. But the part is now we are parameterizing a square. Okay. So when you're parameterizing a square, you want to describe why boundary object is stable, and it turns out every term here is. If you erase any term, I can find a counterexample for you that doesn't work. Okay, let me give you an intuitive picture in the rank 1 case. So so if E is rank 1, then Y is just a hypersurface. So this is a simpler case. So in the rank 1 case, 2 is equivalent to the following. Omega log tensor f fullback of H.
Is H is what?
Ample amount over
Okay, so-
over X. Right, over this X projective variety. So remember that P circle is a vector bundle, so it has a 0 section. And in the rank 1 case, the 0 section happens to be a divisor, so you can put back the divisor class. So in the rank 1 case, we know that 2 equals this, we know that for a long time. And the non-trivial part is how to generalize this expression to the general case, because when E has a higher rank, 0 section isn't a divisor anymore. You can't do that. And what's worse, the bundle E doesn't split, and you don't have any divisor terms except the infinity divisor. So that's why 2 is actually non-trivial. Okay. Sorry, I forgot to tell you that a natural relation needed is K is sufficiently large than M is sufficiently large than 0. And so when you have M divided. So from this relation, you can actually get a delta. That's small numbers. Let me give you an unstable case, which might convince you that this is the right formulation in the rank 1 case. So I take the x on my curve. C is given by P1 with 1 marker point. And I have a differential dx. X is the coordinate around 0. So, so the picture is like this. So here is my 0, which is not a marker point. Infinity is my marker point. And this one is my proj omega log direct sum O. I have infinity section, and I have 0 section. So, so if I use dx, that will give me a section like this. And you'll notice that this dx never intersects the 0 section. And clearly this is unstable because you can move it. It has infinite automorphisms. So the geometry behind the second condition is that if you want something to stable, then you for example, look at the rational tails. If it happened that E splits, you have a lot of divisor to use. Then that rational tail is supposed to intersect with this hyperplane, some hyperplanes, somewhere. And this is the meaning of 2. But this is the best formulation you can find. Okay. So so now let me introduce the stack of R maps.
And so that somehow restricts the automorphism of the curve when you have many rational terms.
Right.
Because
Right.
I know.
Okay, so so this is the stack of stable R maps to the target. I'm not going to specify BC star R because that's universal. With discrete data genus G, you want to specify a tangency condition with infinity. So that's what this is. And if you want to look at the orbifold markings, you can also include the connected components of inertial stacks. But let's focus on the projective varieties. And this one is curve class. Okay, so the first thing is that this stack is a proper elemental log stack. I just want to quickly mention that this one, remember that stable log maps are defined as object over another scheme. So this one is naturally a fiber category over log schemes. And in order to show that this is actually represented by stacks, we need the ACGS, the work from ACGS on stable log maps.
Who is the ACGS?
Abramovich. Mark Ross. Or Siebert. But just this is not enough. So the issue is, remember R maps is a cumulative diagram. The cumulativity is an open condition. So we give examples that without log structure, if you just look at the underlying diagram, the properties definitely fails, no matter what. So somehow prove this one is a proper stack. We need results from here, and we further need to do some work to show that limits exist. Okay, so this gives us the parts of moduli, and now I really want to talk about the virtual cycles. So so I'm going to draw a diagram. So I'm going to consider the stack, the substack inside here, curly P. Yeah. So so this will be substack with imaging in so I'm not taking the full substack, I'm taking the substack where the image of the R map is containing the locus with trivial logarithmic structure. It doesn't touch the infinity that I add to it. Okay. So so now above this we have the universal diagram. PC star R LR and we have so now over this stack we have the ordinary construction. Namely, I take the pullback of the relative tangent bundle. So pullback of the relative tangent bundle governs the deformation of F. And I have a dW to pullback of LR, which is omega log. So in order to apply Kiem-Li cosection construction, this is not enough with omega log. So we need to further restrict it to a locus.
Wait, why do you need to do cosection?
Cosection is how people use to define the virtual cycles in gauge linear sigma model. I want to first give you a gauge linear sigma model, and then show that the compactification recovers it. Okay. So I'm trying to show you the construction of GLSM virtual cycle in the traditional sense.
Because it's not compact.
Because it's not compact.
We want to get a compact locus inside. Very defined size.
So I see. So when you take the cone of the cosection, it corresponds to obstruction theory of compact.
Yeah, you cut off
You cut off the thing that has moving
Exactly.
torus. Okay.
Maybe I'll call it F as well. So now we restrict it to a substack. This has extra constraints on the marker points. So this substack is defined by markings with image in the zero section. Okay. So once I have this, I know that if I constrain the deformation of marking, then Mori already tells us that the deformation theory is given by this. This is very classical, minus the set of markings. So this one factors through a lot because I already subtracted them. So I can have dW. Okay, so then what I'm going to do is the construction discovered by Chen-Li, and many others. So I get H1 of omega is O. But this one is obstruction theory of R. So this one is called the Kiem-Li cosection. So you have a cosection from the obstruction space to O, and then Kiem-Li tells us that
Actually, wait a minute. So shouldn't that dW map to O already?
dW map to which?
Yeah, that one. That should be O. No?
Oh, no. I only twisted on the markings, so I must remove log from this.
Oh,
Okay.
right. Okay,
Okay.
sorry. You're right.
Okay. So let's look at this stack. So this stack has a natural perfect obstruction theory defined by this, or equivalent this. This is the equivalent thing. So that would define us a virtual cycle.
No, so why is it that you have a cosection? Why do you have a map to O?
So this O is pi 1 lower star of omega. I just apply pi 1 R1 pi lower star to this to the bottom.
Right.
That gives me
Okay.
from obstruction to O.
Okay, thank you.
Okay, so this one has a canonical virtual cycle, and this virtual cycle is represented by a child cycle. Now I'm going to write this. which they call cosection localized cycle. And this cycle has a nice property that is supported where the cosection vanishes. But think about where did the cosection come from? Cosection come from dw. And so you could imagine why it relates to a critical locus. And this cosection vanished locus, degenerate locus is precisely the R maps to the critical locus of W. And we've already seen that in the homomorphic Witten case. This will be the stable map to the critical locus. Okay? Which is proper. So the properties of this locus follows from the properties of the critical locus, and that's why we need critical locus of W is proper. Okay, so we start with this stack, which is non-proper because with perma-transit sections we can move it to infinity. That has a virtual cycle. Now realized there's a virtual cycle on a proper locus, so we define an invariance. You can integrate over a proper stack. However, this is hard to compute because the cycle itself, you define the cycle itself uses a non-proper stack. Remember, the proper stack is sections to some bundle, so it has large C-star action, but you cannot use it because the C-star action is going to move things to infinity, so it disappears. So, so the project, so the goal of the project is to find the compactification so that torus localizations again runs and provides interesting things. So, so now with a few minutes left, let me at least state the result. This is theorem with Felix and Run, and based on also based on some previous result with entering. So so there exists a proper subjective morphism. So we call this one a virtual, or maybe more the principalization. Why it's called principalization? I hope I will explain it to you in a minute. So, so I want to emphasize that this is a stack, has modular meaning. This is also a stack with a modular meaning, but this modular meaning is compatible with various constructions. So, so U-compact has a perfect abstraction theory. This leads to a virtual cycle. And this virtual cycle not that different from the virtual cycle of this, because we know that forward property. Okay. So really is a modification. I should say that this proper subjective morphism is iso. So we do not modify the interior of the stack. And this UCPT has a reduced particular abstraction theory. With the property that this reduced class is the cosection localized class. So it recovers the one that we want to recover. Third, so let's look at the boundary. So this one does not modify the interior. So, so let's delete the interior. I want to emphasize that this is not a set theory thing. It has a schematic structure, but let me write it this way. So this one has a reduced virtual perfect obstruction theory. this leads to a reduced virtual cycle. And this virtual cycle has a property that, now I look at the canonical virtual cycle. That is equal to the reduced virtual cycle plus the reduced virtual cycle of this. Okay. So, so why this is useful? Maybe I have 1 more minute. So, application to GW is that, remember previously we said we have S, some sectioning of the bundle E over the projective variety X. This defines the Y, and we want to understand its invariance compared to the invariance of X. Now we give an answer on the level of virtual cycles. So, so it turns out that so what we proved is a reduced virtual cycle is equal to this cosection localized virtual cycle. And there is a lot of work shows that this cosection localized class is actually after assigning the virtual cycle of the remote fitting invariance. So I think this is the first discovered by Chen-Li. And later on, further developed by Kiem-Li, and this Chen and Li, and then Chen and moduli is still not quite young. And the one that most compatible with our setting is a drawing work with physics, web, and also this should be compatible with the work of Qile. Is that you?
Yeah, but
I get it right? Who is here? Okay. So I guess I don't have time to do more things, and I'll stop here.
Any questions for Qile? Next talk is Qile at 2:30. But now we can walk to Science Center to have a lunch.
so, okay, the first, can I?
Yes, of course. You can